Our galaxy is racing through space at an incredible speed. Something with immense power is pulling us, along with countless other galaxies, toward a hidden point in the cosmos. This mysterious force is known as the Great Attractor, and it is just one piece of a vast, invisible architecture that shapes our universe. By the end of this journey, you will understand the 30 greatest secrets behind these cosmic structures and the hidden forces guiding our path. We will uncover why our view of this colossal attractor was blocked for decades and what lies even farther beyond its pull, a discovery that reshaped our entire cosmic address. What does the existence of such a profound and hidden mystery make you wonder about our place in the cosmos? Our own motion through the cosmos was the first clue to something immense and unseen. For centuries, we believed we understood the grand dance of the galaxies, a universe expanding uniformly in all directions. Then, in the 1970s and 80s, a group of astronomers noticed something profoundly wrong. Our galaxy, the Milky Way, was not just drifting apart from others in the cosmic expansion. It was racing with immense purpose toward a specific region of space in the constellation Centaurus. This was not a gentle drift. It was a headlong rush, a river of galaxies all flowing in the same direction against the cosmic tide. The team of scientists who made this stunning discovery, a group so dedicated they were nicknamed the Seven Samurai, had uncovered a fundamental anomaly. The universe was not as smooth or as random as we had thought. A colossal, invisible force was at work, pulling us and everything in our local universe toward a single, mysterious point. The initial reaction was one of deep confusion. How could such a thing exist, and why was it so close to us in cosmic terms? The answer, frustratingly, was hidden in plain sight. The very center of this gravitational pull, the heart of the Great Attractor, lies directly behind the crowded core of our own Milky Way galaxy. This region is known to astronomers as the Zone of Avoidance. It is a thick shroud of cosmic dust, gas, and billions of bright stars that completely blocks our view of the universe beyond. For decades, it was like trying to see a distant mountain range through a dense, permanent fog. We could feel the pull, we could measure its staggering effect on our motion, but we could not see what was doing the pulling. This cosmic blind spot turned a profound discovery into an enduring mystery, forcing us to find new ways to peer through the veil and question everything we thought we knew about the structure of our cosmic neighborhood. That cosmic blind spot, the Zone of Avoidance, became one of the greatest observational challenges in modern astronomy. It was a frustrating paradox. We had compelling evidence for a massive structure, a gravitational monster lurking just out of sight, but our own galactic backyard was in the way. We were like people in a foggy valley, feeling the tremors from a hidden mountain we could not see. To solve this, we needed new eyes that could see the light our own could not. The breakthrough came not with bigger optical telescopes, but with a shift to entirely different parts of the electromagnetic spectrum. We stopped trying to look through the fog and started listening for whispers that could pass through it. Infrared telescopes like the Spitzer Space Telescope changed the game. Cosmic dust is very good at blocking visible light, the kind our eyes see, but it is far more transparent to longer infrared wavelengths. Think of it like this: on a smoky day, you cannot see a distant building with your own eyes, but a thermal camera might pick up its heat signature through the haze. That is precisely what Spitzer did. It peered into the Zone of Avoidance and detected the warm glow of countless stars belonging to galaxies that were completely hidden from our optical view. Then came the X-ray vision of observatories like Chandra. Where infrared sees starlight, X-rays see the most violent and energetic processes in the universe, like superheated gas swirling into supermassive black holes at the centers of galaxies. By mapping these brilliant X-ray beacons, we could trace the skeletons of galaxy clusters hidden behind the Milky Way. Piece by piece, a hidden landscape began to emerge from the shadows. The blank spot on our maps was not empty at all. It was filled with an entire metropolis of galaxies, all bound together by gravity, confirming that the Great Attractor was not a single, bizarre object, but the collective pull of an immense concentration of mass, a vast supercluster of galaxies we were flying toward. This was a triumph of human ingenuity, but it also revealed a much deeper truth. The Great Attractor was real, and it was even more massive than we had feared. So what happens when you finally map the hidden mountain and realize its true, staggering size? The hidden metropolis revealed by our new cosmic eyes held the third great secret. The Great Attractor is not a single, monstrous object in the darkness. It is not a colossal black hole or a lone, impossible star. Instead, it is a vast gravitational focal point, an immense overdensity of matter. Think of it not as a single powerful magnet, but as an entire mountain range. A single magnet pulls, but the combined gravitational pull of every rock, every tree, every ounce of soil in an entire mountain range creates a far more powerful and complex force. That is the true nature of the Great Attractor. It is the gravitational center of a colossal structure, a region of space where the concentration of mass is so great that it dominates the motion of everything around it for hundreds of millions of light years. This overdensity is a cosmic metropolis built from thousands of galaxies, all bound together. It contains vast clouds of mysterious dark matter, an invisible gravitational glue we cannot see but can feel pulling on us. It is filled with enormous reservoirs of superheated intergalactic gas, detected only by their faint X-ray whispers. All of this mass, both seen and unseen, works together. The collective gravity of this entire hidden realm acts as one. It is the weight of this entire cosmic continent that pulls our own galactic neighborhood, the Milky Way included, steadily toward its center. This realization fundamentally changed the mystery. We were not being pulled toward a single, strange anomaly. We were simply following the natural, relentless flow of gravity down the slope of the largest density hill in our local universe. But if this overdensity is so massive, what could possibly lie beyond it that exerts an even greater pull? Just when we thought we had found the ultimate source of the pull, we learned we were looking at the wrong mountain. The discovery of the Shapley Supercluster completely redefined the scale of our cosmic neighborhood. This is not merely another cluster of galaxies. It is the single largest concentration of matter in our entire observable local universe, a true gravitational heavyweight located hundreds of millions of light years beyond the Great Attractor itself. Imagine our previous discovery, the Great Attractor, as a significant hill that was pulling us in. Now, picture discovering an entire Himalayan mountain range behind that hill, its mass so colossal that it is actually the primary force dictating the motion of the hill itself. This is the relationship between the Great Attractor and the Shapley Supercluster. The Great Attractor is a signpost, a waypoint on a much larger cosmic journey. The true engine, the dominant force pulling not just us, but the Great Attractor and our entire local sheet of galaxies, is the immense gravity of Shapley. Its sheer scale is almost incomprehensible. It is a supercluster, a dense knot in the cosmic web containing dozens of massive galaxy clusters and tens of thousands of individual galaxies, all bound together by a gravitational field of staggering power. This realization was a profound shift. Our motion through the cosmos is not dictated by one nearby anomaly, but is part of a vast, river-like flow on a scale we are only beginning to map. So, if Shapley is the primary force, what does that make the Great Attractor, and how does this change our cosmic address? This immense gravitational power translates into a velocity that is almost impossible to fully comprehend. Our entire local group of galaxies, a collection that includes our Milky Way and our great neighbor Andromeda, is being pulled toward the Great Attractor at a staggering speed of over 600 kilometers every single second. To put that into a more familiar perspective, that is roughly 1.3 million miles per hour. You are currently on a planet orbiting a star inside a galaxy that is moving through the void at 1,000,000 miles an hour toward a hidden cosmic destination. It is a motion you cannot feel, a speed you cannot perceive, yet it is the true trajectory of our galactic home. This is not a gentle drift, it is a relentless cosmic current. Imagine floating on a quiet, peaceful river. The water around you seems still, but when you look toward the riverbank, you realize you are moving with a powerful, silent force. That is what this is like, but on a scale so vast the river is made of galaxies, and the current is the unwavering flow of gravity itself. This incredible speed is the most direct measurement we have of the Attractor's hidden strength, a constant reminder that even the emptiness of space is alive with motion, guided by the invisible hand of mass. So what other invisible currents are flowing through the cosmos, and how do they shape the universe on the largest scales? This silent 1,000,000-mile-an-hour journey finally found its context with a discovery that redefined our home. For centuries, we thought our Milky Way belonged to the Virgo Supercluster, a simple collection of galaxy groups, but that map was incomplete, missing the true gravitational currents that truly define our place in the cosmos. The breakthrough came when a team of astronomers decided to stop just looking at where galaxies are, and instead started mapping how they move. They meticulously charted the velocities of thousands of galaxies, tracing the subtle flows and streams against the backdrop of the universe's expansion. What they revealed was our true cosmic continent, a structure of almost unimaginable scale that they named Laniakea, a Hawaiian word meaning immense heaven. Laniakea is our home supercluster. It is not simply a group of galaxies that happen to be near each other. It is a single, coherent river system, a vast network of galactic motion, all flowing toward a single, powerful gravitational center. And what is that center? The great basin into which all these rivers of stars pour. It is the Great Attractor itself. All the motion we have been discussing, our own headlong rush and that of our neighboring galaxies, is simply the local expression of this much larger flow. The Great Attractor is not a distant anomaly we are approaching. It is the beating heart of our own cosmic home, the central point that holds the entire structure of Laniakea together. Our supercluster spans over 500 million light-years and contains more than 100,000 large galaxies. Every single one of them, including our own, is on a long-term orbital path, a slow, cosmic dance around this hidden gravitational core. This means our cosmic address is far grander than we ever knew. We do not just live in the Milky Way galaxy. We live in the Laniakea Supercluster, a domain whose shape and destiny are governed by the immense, unseen pull of the Great Attractor. So if this is the true shape of our home, what defines its borders and what lies just beyond its shores? But the true power behind this immense structure comes from something we cannot see at all. The Great Attractor's overwhelming gravity does not primarily come from the thousands of galaxies we have painstakingly mapped. Those brilliant cities of stars are merely the visible lights on a far deeper, invisible framework. The real engine, the hidden source of the pull that defines our entire supercluster, is a colossal halo of dark matter. This mysterious substance is the universe's greatest secret. It emits no light, no radiation, no signal we have yet been able to capture directly. We only know it exists because of its profound gravitational influence on everything we can see. Think of it like this: if the Great Attractor were a massive, spinning Ferris wheel, the glowing galaxies would be just the light bulbs attached to its struts. The dark matter is the heavy, black iron frame itself, the underlying structure that gives the whole wheel its strength, its shape, and its powerful grip. This invisible scaffold is what truly pulls on the visible universe. It guides the flow of superheated gas, it dictates the motions of galaxy clusters, and it creates the gravitational basins that define superclusters like our own Laniakea. Without this dark matter engine, the collective gravity of all the stars and gas we can observe would be far too weak to account for the million-mile an hour current we are riding. This means we are not just being pulled by the mass we have found. We are being guided by the ghostly hand of an unseen universe, a hidden reality that makes up roughly 85% of all the matter in existence. So if dark matter is the true cosmic architect, what other invisible structures has it built across the void? This invisible cosmic architecture reveals itself on the grandest scale of all. The universe is not a random scatter of galaxies, nor is it a uniform soup. Instead, it forms an intricate, colossal structure known as the cosmic web. Picture the universe as it truly is, a vast network of interconnected filaments, like the delicate threads of a spider's web spun across unimaginable distances. These filaments are the superhighways of the cosmos, long, twisting rivers of dark matter and galaxies that stretch for hundreds of millions of light years. Where these filaments intersect, they create dense, powerful knots. These are the superclusters, the great metropolitan hubs of the universe, and between these brilliant strands lie the cosmic voids, immense, nearly empty deserts of space so vast they can span hundreds of millions of light years across. This is the large-scale structure of everything, a pattern born from the subtle gravitational imbalances of the early universe, amplified over billions of years. So where does our own journey and the Great Attractor fit into this cosmic map? The Great Attractor is not merely the heart of Laniakea. It is one of these major nodes, a critical intersection point within the universal web. It is a place where several of the cosmos's largest filaments converge, pouring galaxies and dark matter into a singular, massive gravitational well. Our entire Laniakea supercluster is essentially this local knot in the web, with the Great Attractor as its central hub. We are not just flowing toward it, we are part of the web itself, caught in the flow along one of its grandest strands, moving toward a junction that connects us to the rest of the cosmic network. This changes the perspective entirely. Our million-mile and hour motion is not a solitary journey. It is the predictable gravitational flow of matter along a cosmic filament, heading toward a dense node, just as water flows downhill toward a lake. The Great Attractor is that lake, a gathering point for the galactic rivers flowing through the web. This realization connects our local mystery to the universe's deepest architecture. If this web is the true shape of the cosmos, what could have possibly woven it in the first place? The cosmic web weaves patterns of staggering complexity, but some of its threads are so vast they challenge the very foundations of cosmology. One such structure is the Sloan Great Wall, a filament of galaxies so immense it was, for a time, the single largest known object in the entire observable universe. Discovered in 2003 using data from the Sloan Digital Sky Survey, this colossal formation is not a simple line of galaxies. It is a massive, interconnected sheet, a great curtain of matter stretching for over 1.3 billion light-years across the cosmos. To grasp that scale, consider the journey of a single photon of light, the fastest thing in the universe. It would take that particle over 1 billion years just to travel from one end of this wall to the other. This is not merely a large object, it is a fundamental feature of the cosmic landscape, a mountain range on a truly universal scale. Its very existence sends ripples through our understanding. For decades, a core principle of cosmology has been the cosmological principle, the idea that on the largest scales, the universe is smooth and homogeneous. It should look roughly the same from every vantage point, with matter distributed evenly when you zoom out far enough. The Sloan Great Wall directly challenges that assumption. A structure of this magnitude should not, according to some models, be able to form in the time since the Big Bang. Its scale seems to push against the theoretical limits of how quickly gravity can pull matter together across such vast distances. Finding it was like mapping a single continent so large it seemed to cover a significant portion of the entire globe. forcing us to reconsider the rules of cosmic geography. If structures this colossal can exist, what does that say about the uniformity of our universe, and what other impossibly large formations might be waiting to be found? The Sloan Great Wall seemed to defy the very rules of the cosmos, but an even stranger motion was detected in the depths of space, one that pointed to forces beyond our universe. Astronomers studying the faint afterglow of the Big Bang, the cosmic microwave background, made a startling discovery. They found that hundreds of distant galaxy clusters were streaming in a coherent, uniform direction at incredible speeds. This was not the local flow toward the Great Attractor or the pull of Shapley. This was something else entirely, a motion on such a vast scale that it had no explanation within our observable universe. They called this phenomenon the dark flow. The name itself hints at the deep mystery. It suggests a current driven not by the mass we can see or the dark matter we can infer, but by something entirely unknown, something whose gravitational pull originates from beyond the edge of everything we can see. The most radical theory proposed to explain the dark flow is as breathtaking as it is controversial. What if this motion is evidence of a multiverse? The idea suggests that the immense gravitational tug could be coming from another universe entirely, a separate cosmic bubble floating in a wider multiversal sea, its mass pulling on our own universe like a distant magnet. This is not a settled fact, far from it. The very existence of dark flow is hotly debated within the scientific community. Some argue the data is a statistical fluke or an artifact of measurement. Yet, if it is real, it implies that our entire cosmos, all hundreds of billions of galaxies, might be drifting as one towards something we can never see, a destination outside our own reality. This raises a profound question. If we are caught in a dark flow, what other invisible shores might lie in the great beyond? These immense cosmic filaments and walls define the universe, but they are only half the story. Between them lies nothingness on a scale that defies human comprehension. These are the cosmic voids, the vast, empty deserts of space that form the other essential part of the cosmic web. If the web's filaments are the continents of the universe, then the voids are the empty oceans between them. But these are not small gaps. A single cosmic void can span 300 million light-years or more, regions of space so profoundly empty that they might contain only a handful of isolated galaxies, lost in an immensity of near-total blackness. This emptiness is not passive. It plays a crucial role in shaping the motion of everything we see. Think of the universe as a landscape of hills and valleys, where the hills are the dense superclusters and the valleys are these deep, empty voids. Gravity works in both directions. It not only pulls matter toward the dense hills like the Great Attractor, but it also pushes it away from the empty valleys. The voids are actively repelling galaxies. Because there is so little mass inside a void, its gravitational pull is incredibly weak. The stronger gravity from the surrounding matter-rich filaments pulls galaxies outward, effectively emptying the void even further. This creates a powerful cosmic tide, a suction effect that helps channel and accelerate galaxies toward the Great Attractors and Superclusters. Our own journey toward the Great Attractor is partly driven by this push from the void behind us. We are not only being pulled by the immense mass ahead, but we are also being pushed by the profound emptiness we leave behind. This intricate balance between the something and the nothing is what gives the cosmic web its structure and drives the eternal flow of the galaxies. So, if voids can actively repel matter, what happens when a galaxy gets stranded in the middle of one of these cosmic deserts? These galactic superclusters are the true continents of our cosmos, the largest structures that gravity can bind together. A supercluster is not a simple, tight-knit family of stars. It is a sprawling metropolis of galaxies, a vast collection of galaxy clusters and groups all loosely connected by their mutual gravitational pull. Within a supercluster, thousands of individual galaxies, each with billions of stars, are organized into smaller neighborhoods called groups and clusters, and these neighborhoods are then strung together along the filaments of the cosmic web into one immense, coherent structure. Before we understood our place in Laniakea, we believed our home was the Virgo Supercluster, a smaller collection centered on the massive Virgo cluster of galaxies. But Virgo is just one province within the far grander domain of Laniakea. Other notable superclusters populate our local universe, each a titan in its own right. The Hydra Centaurus supercluster, for instance, lies along the same cosmic filament that leads toward the Shapley Supercluster, acting as a stepping stone in the great gravitational flow we are part of. The true power of these structures lies in their gravitational interactions. They are not static islands in space. They are dynamic, constantly tugging on one another across the millions of light years that separate them. In our local cosmic neighborhood, the gravitational landscape is dominated by two colossal players. The Great Attractor acts as the central hub of our own Laniakea supercluster, pulling all its member galaxies into a shared orbit. But Laniakea itself, in its entirety, is caught in the even more powerful gravitational field of the Shapley Supercluster. This creates a hierarchy of influence, a cosmic dance of titans where Shapley pulls on Laniakea, and Laniakea, centered on the Great Attractor, pulls on us. We are witnessing the fundamental process that builds the universe, where smaller structures merge and flow into larger ones, drawn together by the relentless, invisible force of gravity. If these are the continents, what does their long-term fate tell us about the ultimate destiny of the cosmic web itself? This growing map of cosmic flows has led us directly to one of the most profound puzzles in modern science, a mystery known as the Hubble tension. At its heart is a simple, fundamental question. How fast is the universe expanding? For decades, we assumed we had a good handle on the answer, but now our most precise measurements are telling two conflicting stories. One story comes from our local cosmic neighborhood. We use what are called standard candles, stars like Cepheid variables whose known brightness allows us to measure distances with incredible accuracy. By observing these stars in nearby galaxies, we can calculate the local expansion rate of space, a value known as the Hubble constant. The other story comes from the very beginning of the universe, imprinted on the cosmic microwave background. This ancient light gives us a snapshot of the infant cosmos, and by applying our best models of cosmic evolution, we can predict what the expansion rate should be today. The problem is stark. These two numbers do not match. The local measurement suggests the universe is expanding significantly faster than the early universe data predicts. It is as if you carefully calculated how fast a car should be going based on its engine's power, but then you clocked it with a radar gun and found it was moving much quicker. This discrepancy is not a small error. It is a significant gap that has withstood years of rechecking and improved observations, implying there might be something fundamentally wrong with our standard model of cosmology. So where does our journey toward the Great Attractor fit into this? The key lies in a concept called peculiar velocity. This is the motion of a galaxy that is not due to the overall expansion of the universe. It is the extra speed, the local current, caused by the gravitational tug of nearby massive structures. Our own million-mile and our motion toward the Great Attractor is a perfect example of a peculiar velocity. When astronomers try to measure the true, pure expansion rate of the universe using nearby galaxies, they must first subtract out all these peculiar motions. If we misjudge the strength of a local gravitational pull like the Great Attractors, or if there are other vast, unseen flows we have not accounted for, our calculation of the local expansion rate becomes skewed. It is like trying to measure a steady river current while you are floating in a powerful, local whirlpool. If you do not correctly account for the whirlpool's spin, you will get the speed of the river completely wrong. The Hubble tension, therefore, forces us to ask a critical question. Is the tension real, pointing to new physics or exotic dark energy? or is it simply a reflection that our map of cosmic flows from the Great Attractor to even larger structures is still incomplete? Resolving this mystery depends on understanding every last ripple in the river of galaxies. This silent million-mile-an-hour journey through the cosmos leaves its mark on the oldest light in the universe. The cosmic microwave background, that faint, cold glow that fills all of space, is the cooled remnant of the Big Bang's fireball. It is our most pristine map of the infant universe, and it carries a subtle, telltale signature of our motion. When astronomers first mapped this background radiation with incredible precision, they expected to see a perfectly uniform temperature in every direction, a final echo of a once smooth cosmos. But they found a distinct pattern, a phenomenon called the CMB dipole. One half of the sky appears ever so slightly warmer, while the opposite half appears just a fraction colder. This is not a flaw in the data, it is a cosmic speedometer. The explanation is remarkably similar to everyday experience. Imagine standing still in a gentle rain, and the drops fall straight down on you evenly from all directions. Now start running. As you move forward, you will feel more raindrops hitting your front than your back. The rain seems to be coming at you from ahead. This is the Doppler effect in action, and the same principle applies to light. Because our galaxy is rushing through space toward the Great Attractor, we are moving into the cosmic microwave background radiation from that direction. The light waves from ahead are compressed, making them appear slightly warmer or more energetic. The light from behind us is stretched, making it appear just a bit colder. This temperature difference is the CMB dipole, and it is one of the most fundamental validations of our motion. It confirms that our headlong rush is not a local illusion. It is a real velocity through the fabric of space itself, an absolute motion measured against the backdrop of the universe's first light. This ancient echo not only tells us we are moving, but it points directly to where we are going, aligning perfectly with the direction of the Great Attractor's pull. So if this universal backdrop can chart our course, what other secrets about cosmic motion might it still be hiding? Our current trajectory feels so certain, a million-mile-an-hour rush toward a cosmic heart. Yet this journey has a surprising and counterintuitive ending. We will never actually reach the Great Attractor. The ultimate fate of our galaxy is not a dramatic collision with this gravitational giant, but a slow, eternal dance around it, governed by two opposing forces locked in a cosmic tug-of-war. On one side is the relentless pull of gravity, the force that binds our local group and the entire Laniakea Supercluster together. This pull ensures we are permanently connected to the Great Attractor, forever caught in its immense gravitational well. We are not just passing by, we are a permanent part of its celestial kingdom, destined to orbit this hidden center for billions of years. But the other force, the mysterious dark energy driving the universe's expansion, is even more powerful on the largest scales. As the universe continues to expand at an accelerating rate, the vast distances between the great cosmic structures are being stretched. The space between superclusters themselves is growing. This means that while our local group of galaxies will remain gravitationally bound, forever orbiting within Laniakea, the entire Laniakea Supercluster will become increasingly isolated from other structures like the Shapley Supercluster. We are like a group of boats tied together in a harbor, rising and falling with the local tides, while the entire ocean around us expands, carrying other harbors away over an unreachable horizon. So our destiny is one of cosmic belonging, not of conquest. We are forever a part of this great supercluster, our motion a perpetual orbit around the unseen heart that guides us, even as the rest of the visible universe slowly recedes into darkness. Deep within the gravitational heart of our supercluster lies a hidden metropolis of stars. This is the Norma cluster, also known as ACO 3627, the true core of the Great Attractor. For so long, this entire region was a blank spot on our maps, but we now know it is one of the most massive and dense collections of galaxies in our entire cosmic neighborhood. Imagine a city so packed with skyscrapers that their lights blend into a single, brilliant glow from a distance. The Norma cluster is the galactic equivalent, a rich, sprawling city of galaxies where thousands of these star systems are bound together by their immense collective gravity. What would it be like to exist inside such a place? The environment is far more extreme than our own quiet galactic suburb. Galactic collisions and close encounters are common, triggering furious bursts of new star formation and feeding the supermassive black holes that lurk at the centers of many galaxies. The space between the galaxies is not empty, but filled with a superheated plasma, a thin, incredibly hot gas that radiates powerful X-rays, a permanent testament to the intense gravitational pressures at work. This is not a peaceful realm. It is a dynamic, chaotic, and vibrant cosmic hub, and its sheer mass is the primary source of the gravitational anchor that holds our entire Laniakea Supercluster together. So if this bustling cluster is the true heart of the Great Attractor, what other hidden giants might be living in this crowded galactic city? The true scale of our cosmic home becomes clear only when we step back even further. Beyond the familiar boundaries of Laniakea lies a structure so vast it makes our superclusters seem like a single neighborhood in an entire galactic nation. This is the Pisces-Cetus Supercluster complex, a name that hints at its sprawling majesty. It is not merely another supercluster, but one of the largest known filamentary structures in the entire observable universe, a great arc of interconnected superclusters stretching across 1 billion light-years of space. Within this immense complex, our own Laniakea Supercluster is just one constituent part, a single branch on a cosmic tree of staggering proportions. This represents the next hierarchical level of cosmic organization. First, we have individual galaxies. These galaxies gather into groups and clusters. Those clusters then form superclusters like Laniakea. And finally, these superclusters themselves link together into these colossal complexes, the largest structures that gravity can still weakly bind across the expanding cosmos. The existence of the Pisces-Cetus complex reveals a universe built like a nested set of Russian dolls, each level of structure contained within a larger, more encompassing one. It shows us that the cosmic web is not just a random tangle of threads, but a highly organized, hierarchical network where every galaxy, every cluster, and every supercluster is part of a grander flow, a pattern written into the fabric of reality since the first moments of time. If our local journey is governed by the Great Attractor, what immense, slow-moving currents within this billion-light-year complex are guiding its ultimate destiny? Frozen into the fabric of the cosmos is a ghostly ruler, a relic from a time when the universe was a seething, liquid-like plasma. This is the secret of Baryon acoustic oscillations, a concept with a complex name that describes a beautifully simple cosmic imprint. To understand it, we must travel back to the universe's first 400,000 years. At this time, space was not transparent. It was a hot, dense fog of particles, a soup of light and matter so thick that photons of light were constantly bouncing off electrons, trapped in a relentless push and pull. In this primordial fluid, gravity was constantly trying to pull matter together into dense clumps, but the intense pressure of the light radiation was pushing it all apart. This created a tug-of-war that sent powerful sound waves, literal pressure waves, racing outward through the cosmic fluid at over half the speed of light. Then, in an instant, the universe cooled just enough for atoms to form. The fog cleared. Light, which had been trapped for so long, was suddenly set free, streaming across the universe to eventually become the cosmic microwave background we detect today. And the matter that had been gathered at the leading edge of those rushing sound waves was frozen in place, left behind as a permanent spherical shell. This is the Baryon acoustic oscillation. Imagine a single, powerful pebble dropped into a still pond, sending out a perfect circular ripple. Now imagine that the pond instantly freezes solid, preserving that ripple forever. That is what happened to the entire universe, but with trillions of pebbles, creating a universe-sized fossil of those first cosmic sounds. This fossilized ripple has a very specific known size. It spans about 500 million light-years across, a distance so vast it serves as a perfect standard ruler etched across the sky. By spotting this known scale in the distribution of galaxies today, astronomers can perform incredible feats of cosmic measurement. Massive surveys like the Sloan Digital Sky Survey map the positions of millions of galaxies, searching for this telltale pattern. This subtle statistical preference for galaxies to be separated by that specific 500 million light-year distance. When they find it, they can measure how much this standard ruler appears stretched or compressed by the expansion of the universe and the gravitational pull of immense structures. This allows them to weigh colossal formations like the Great Attractor with unprecedented precision, calculating the total mass, both visible and dark, required to create its gravitational pull. Even more profoundly, by tracking how this standard ruler has changed over cosmic time, we can measure the accelerating push of dark energy itself, the very force that dictates the ultimate fate of our cosmic web. The same gravitational pull that defines our cosmic home is locked in a silent war with a force of pure repulsion. Dark energy is the counterweight to the Great Attractor, a mysterious presence that permeates the very vacuum of space itself, pushing the universe apart. While gravity tirelessly works to pull matter together, weaving galaxies into clusters and superclusters, dark energy acts on the largest scales to tear this cosmic web asunder. Its effect is not a gentle nudge but an accelerating push, a force that grows stronger as the universe expands and empties, driving the cosmos toward a future of ultimate isolation. This fundamental opposition sets a limit on the size of everything we see. Without dark energy, gravity would continue to pull more and more matter into ever larger structures over countless eons. Superclusters would merge into hyperclusters of unimaginable scale. But dark energy has slammed the brakes on this cosmic consolidation. The vast, empty voids between the web's filaments are not just empty, they are expanding at an ever-increasing rate, stretching the space between superclusters like a rubber sheet being pulled taut. This means the great rivers of galaxies flowing toward attractors like our own are, in the grandest scheme, fighting a losing battle. The local pull of gravity may win within our supercluster, binding us to Laniakea forever, but on the inter-supercluster scale, dark energy is the ultimate victor. It determines that structures like the Pisces Cetus complex will never fully coalesce into a single, bound entity. The cosmic web is not a permanent fixture, but a temporary, beautiful pattern, destined to be stretched and diluted over time. So if dark energy is steadily winning this cosmic tug-of-war, what does that mean for the long-term future of every galaxy, every star, and every structure we see in the night sky? Our journey to map the hidden mountain depended on learning to see in colors invisible to human eyes. Each wavelength of light tells a different part of the story, and by combining them all, we have finally assembled a complete portrait of the Great Attractor. X-ray observations were the first to reveal the true scale of its power. Orbiting observatories like Chandra peered into the Zone of Avoidance and detected a diffuse, superheated glow. This is the signature of intergalactic gas, heated to millions of degrees, swirling within the immense gravitational well of the Norma cluster and its surroundings. This hot plasma is a direct tracer of mass, marking where the deepest gravitational potentials are located. Where there is that much hot gas, there must be a colossal amount of gravity holding it there. While X-rays show us the searing heat of trapped gas, infrared light pierces the cosmic dust to show us the cold birth of stars. Telescopes like Spitzer and Herschel looked toward the attractor and saw a faint, warm glow where our optical telescopes saw only darkness. This is the light from countless newborn stars, their formation hidden within dense clouds of dust in the many galaxies of the region. It revealed that the Great Attractor is not a static structure, but a vibrant, dynamic region where galaxies are actively building new generations of stars, their creation shrouded from our ordinary sight. And then there is the silent whisper of radio waves. Giant radio telescopes like the Parkes Observatory in Australia can map the distribution of neutral hydrogen gas, the raw material for stars that permeates the space between galaxies. By measuring the subtle shifts in the radio emission from this hydrogen, astronomers can trace the precise motions of galaxies hidden behind the Milky Way, confirming their membership in this vast, flowing river of matter. Together, these different views form a single, coherent image. The X-rays outline the immense gravitational skeleton, the infrared reveals the hidden life within, and the radio waves map the silent, flowing currents. We are no longer blind to the Great Attractor. We see it in all its violent, beautiful, and multifaceted complexity. So if we can now see this hidden heart, what other secrets about its past and future might these different wavelengths reveal? This silent push from the void is a force felt across the cosmos, but one desert of emptiness stands out as truly alien. The Boots Void is a spherical region of space so profoundly empty it has earned the nickname the Great Nothing. Stretching an almost unbelievable 330 million light-years across, this void is not merely a gap between galactic filaments. It is a cosmic chasm of staggering proportions, a hole in the universe where the expected metropolis of thousands of galaxies has been almost entirely erased. If you were to place our Milky Way at its center, the nearest edge of this emptiness would be a journey of 165 million light-years through near-total blackness before you encountered a significant wall of galaxies. The sheer scale of this nothingness defies easy explanation. How could a region this vast, born from a universe that was supposedly quite uniform in its infancy, end up so empty? The leading theory suggests it is simply a vast underdensity, a colossal fluctuation in the primordial universe where, by sheer chance, very little matter coalesced. Over billions of years, the weaker gravity within the void and the stronger pull from the surrounding superclusters actively siphoned away the few galaxies that may have once called it home, leaving behind a near-perfect vacuum. But its immense size pushes the limits of this idea, leading to more exotic proposals. Some have wondered if the Boots Void is the result of an unimaginable cosmic collision in the earliest moments of time, or even the footprint of something else entirely. Yet for all its strangeness, the Boots Void is not an error in the cosmos. It is the essential, active counterpart to the Great Attractors. These voids are not passive backgrounds. They are dynamic entities whose repulsive gravity helps sculpt and accelerate the great flows of galaxies toward dense nodes like our own Laniakea. The Great Attractor pulls and the great voids like the one in Boots push. This delicate balance between something and nothing is what gives the cosmic web its intricate structure and drives the eternal motion of the galaxies. What other profound emptiness might lie beyond our current maps, silently shaping the destiny of the universe? The very fabric of space itself becomes our telescope when we learn to read its curves. This is the secret of gravitational lensing, a phenomenon predicted by Einstein where the gravity of a massive object warps the space around it, bending the path of light from more distant galaxies behind it. It is nature's ultimate scale, allowing us to weigh what we cannot see. When astronomers point their telescopes toward the Great Attractor, they are not just looking at the galaxies they can detect. They are searching for subtle distortions in the light from galaxies billions of light-years farther away. As this ancient light journeys toward us, it passes through the immense gravitational field of the attractor. The combined mass of all its dark matter, hot gas, and thousands of galaxies acts like a vast, lumpy lens, twisting and magnifying the images of the background galaxies in a telltale way. These distortions are incredibly faint, like looking at a distant street lamp through the rippling heat rising from a hot road. But by analyzing the shapes of millions of these background galaxies, sophisticated computer algorithms can work backward. They can decipher the precise pattern of the warping to create a detailed map of the total mass responsible for it, a map that includes every ounce of both visible and invisible matter. This is how we truly weigh the Great Attractor. The resulting mass map reveals the hidden skeleton of our supercluster. It shows the colossal halo of dark matter that forms the true gravitational core, a vast, invisible cloud whose pull far outweighs the combined mass of all the brilliant galaxies we can observe. This technique confirms that the Great Attractor's power comes not from starlight, but from this unseen gravitational anchor, proving that the largest structures in the universe are built and shaped by the hand of the dark. So if we can map this hidden mass so precisely, what does its specific shape tell us about how our cosmic home first came to be? Deep within the turbulent heart of the Norma cluster, at the center of nearly every major galaxy, lies a silent gravitational monster. These are the supermassive black holes, and while their immense gravity is confined to their own galactic domains, their influence radiates outward, shaping the entire environment of the Great Attractor. Each of these cosmic engines is a paradox, an object of ultimate collapse that can also become a beacon of incredible energy. When vast amounts of gas, dust, and stars are pulled into the accretion disk swirling around a black hole, the material does not simply vanish. It is superheated to millions of degrees and, in a tremendous release of power, can be blasted back out into space in the form of searing radiation and colossal jets of plasma that travel at nearly the speed of light. This process is known as active galactic feedback, and it is a crucial force within the crowded core of our supercluster. Imagine a bonfire in the middle of a frozen lake. The fire itself is localized, but the heat it radiates can melt the ice for meters around, changing the very nature of its immediate environment. On a cosmic scale, that is what these black holes do. Their high-energy jets punch far out into the space between galaxies, a region known as the intracluster medium. This space is not a perfect vacuum. It is filled with a thin, superheated gas that is the key to future star formation. When the black hole's jets slam into this gas, they transfer enormous energy, stirring it up and heating it even further. This has a profound regulatory effect. If this intergalactic gas were allowed to cool and condense peacefully, it would flow into galaxies and fuel the birth of billions of new stars, but the black holes prevent that. By keeping the gas hot and turbulent, they effectively put a lid on star formation, governing the growth of their own galaxies and their neighbors. This feedback creates a delicate cosmic balance, a self-regulating cycle where a galaxy's own central black hole controls its ultimate size and brightness. So, within the Great Attractor, these hidden monsters are not just passive anchors. They are active architects, using their furious energy to sculpt the galactic metropolis and dictate the rhythm of cosmic life and death. Measuring the universe requires a ladder built from overlapping steps of certainty. We cannot simply stretch a tape measure across the void, so astronomers have constructed a brilliant sequence of methods called the cosmic distance ladder. Each rung of this ladder depends on the one below it for calibration, creating a chain of measurements that reaches from our solar system to the edge of the observable cosmos. The first rung is built on simple geometry, using the Earth's orbit as a baseline to measure distances to nearby stars through stellar parallax. This is like viewing your thumb with one eye closed, then switching eyes and seeing it jump against the background. That apparent shift when measured for a star gives us a direct, reliable distance. With these nearby stars firmly placed, we can identify a special class of pulsating stars called Cepheid variables. These stars are our next critical rung. Their true brightness is directly tied to their pulse rate, so by measuring how fast they brighten and dim, we know their intrinsic power. Comparing that known brightness to how dim they appear from Earth reveals their distance with remarkable precision. Cepheids become standard candles, allowing us to leap across millions of light years to measure distances to other galaxies. And within those galaxies, we can observe another, even brighter standard candle, a specific type of stellar explosion known as a Type Ia supernova. These explosions are so uniform in their peak brightness that they act as cosmic beacons, visible across billions of light years, allowing us to calibrate the final, highest rungs of the ladder and measure the expansion of the universe itself. This entire, intricate structure is what allows us to map the cosmos. But what happens when there is even the slightest uncertainty in one of these rungs? The entire ladder can sway. A tiny error in the distance to a single, crucial Cepheid variable star can propagate upward, distorting our measurement of a supernova's distance, which in turn skews our calculation of the Hubble constant, the very rate of cosmic expansion. This is where the mystery of the Great Attractor becomes deeply entwined with the stability of our cosmic tools. To detect its pull, we do not just need to know where a galaxy is, we need to know how it is moving relative to the pure expansion of space. We calculate this peculiar velocity by comparing the galaxy's measured redshift, its motion away from us due to expansion, with its predicted redshift based on its independently measured distance from the distance ladder. A discrepancy reveals the galaxy's true motion through space, the extra push or pull from local gravity. If our distance measurement is off by even a small percentage, our calculation of that galaxy's peculiar velocity is wrong. We might mistake a galaxy that is actually being pulled toward the attractor for one that is simply drifting with the cosmic tide, or vice versa. This means the strength and reach of the Great Attractor's influence, and even the existence of larger flows like the dark flow, hinge on the absolute integrity of every single rung in our cosmic distance ladder. How can we be certain our measurements are not leading us toward a gravitational phantom? Even our most ambitious maps of the cosmos can be suddenly rendered incomplete. Just when the Sloan Great Wall seemed to define the upper limit of size, an even more colossal formation emerged from the darkness, challenging our understanding of cosmic structure itself. This is the Hercules Corona Borealis Great Wall, a contender for the single largest known structure in the entire observable universe. Its scale is so immense it seems to defy the very laws that govern cosmic evolution. While the Sloan Great Wall is a staggering 1.3 billion light-years across, the Hercules Corona Borealis Great Wall may stretch for over 10 billion light-years, a distance that represents a significant fraction of the observable universe's total diameter. We did not find this behemoth by looking for galaxies. Its discovery was an act of cosmic deduction, made possible by mapping the most violent explosions since the Big Bang. Astronomers were studying gamma-ray bursts, the final, catastrophic detonations of massive stars. These brilliant flashes are so powerful they can be seen across the universe, and they serve as rough markers for the locations of galaxies. When scientists plotted the positions of these bursts, they noticed an astonishing concentration. A vast, curving arc across the constellations of Hercules and Corona Borealis was filled with an unexpected number of these cosmic beacons, implying the presence of an unimaginably large, dense wall of galaxies that was causing a frenzy of star formation and stellar death. This was the ghostly outline of the Great Wall. Its existence sends even deeper tremors through the foundation of cosmology than the Sloan Great Wall did. The cosmological principle, the bedrock assumption that the universe should look roughly the same from every vantage point when viewed on a sufficiently large scale, is pushed to its absolute breaking point. A structure 10 billion light-years in size cannot be considered a mere local fluctuation. It is a fundamental feature of the cosmic landscape, a continent so vast it seems to contradict the idea of a smooth, homogeneous universe. If such a gigantic formation can exist, what does it say about the initial conditions of the Big Bang? Could the seeds of this immense structure have been planted in the first moments of time? And what other impossible giants might be lurking in the unexplored regions of our cosmic maps? These colossal walls and voids are not just random patterns, but the predictable outcome of universal laws. To understand how a nearly smooth infant cosmos could evolve into the intricate cosmic web we see today, we turn to the digital universe. Inside the world's most powerful supercomputers, scientists run some of the most complex simulations ever conceived, recreating the entire history of the universe from its first moments to the present day. One of the most famous of these is the Millennium simulation. It does not just model a few galaxies, it tracks the gravitational dance of more than 10 billion particles of dark matter across a virtual space over 2 billion light-years wide, following their evolution for over 13 billion years of cosmic time. The simulation begins with conditions just after the Big Bang, a universe that is almost but not perfectly smooth. It seeds this digital cosmos with the tiny fluctuations in density we observe in the cosmic microwave background. Then it lets the laws of physics take over. The relentless pull of gravity acts on these minor imperfections. Over billions of virtual years, dark matter, influenced only by gravity, begins to clump together, forming an invisible scaffolding. Ordinary matter, the gas that will become stars and galaxies, then flows along this pre-existing dark matter framework, pooling in the densest knots and streaming along the emerging filaments. The result is breathtaking. When the simulation reaches its end point corresponding to our modern universe, it displays a vast cosmic web. There are the long, twisting filaments, the dense clusters at their intersections, and the vast, empty voids between them. It is a structure that looks remarkably like the real maps we have painstakingly created from telescope surveys. Even more astonishingly, when astronomers analyze their virtual universe, they find structures that behave just like our own Great Attractor. The simulation naturally generates these massive gravitational focal points, regions where the flow of thousands of virtual galaxies is directed toward a central, dominant node. This is a profound validation. The fact that our mathematical models, when given the correct starting conditions and the known laws of physics, can successfully grow a universe that looks and behaves like our own, gives us tremendous confidence that we are on the right track. It tells us that the Great Attractor is not a bizarre anomaly, but a natural and expected feature in a cosmos governed by dark matter and dark energy. So if our digital twins can so accurately recreate the cosmos we see, what other hidden chapters of our universe's history might they be able to reveal? The grand cosmic web, with all its magnificent filaments and clusters, faces a slow and certain dissolution. Billions of years from now, the delicate balance that built our universe will be irrevocably broken. Dark energy, the mysterious force driving the accelerating expansion of space, will become the universe's dominant architect. Its repulsive push will grow stronger as the cosmos becomes emptier, overwhelming the local pull of gravity that holds structures like our Laniakea Supercluster together. The great rivers of galaxies flowing toward the Great Attractor will gradually slow, then halt, and finally reverse. The intricate network of filaments will stretch and thin, like a watercolor painting left in the rain, its beautiful patterns blurring into a featureless wash. Superclusters will be the first to lose their coherence. The gravitational bonds that loosely tie them together are no match for the relentless stretching of space itself. Our own Laniakea, with the Great Attractor at its heart, will slowly unravel. The galaxies within it will no longer share a common orbital destiny. They will drift apart, their shared motion fading into memory as the space between them expands at an ever-increasing rate. Next, the smaller galaxy clusters and groups will be torn apart. Even the tight-knit family of our local group, which includes the Milky Way and Andromeda galaxies, will eventually feel the strain, though its bonds are far stronger. Over trillions of years, the cosmic landscape will transform into a sea of isolated island universes. Each galaxy will be surrounded by an ever-widening gulf of nothingness, the light from all others having long since faded beyond the visible horizon. In this distant future, the very concept of a large-scale structure will become meaningless. the Great Attractor will be a ghost, its gravitational influence dissolved into the void. There will be no more flows, no more currents, no more grand attractors or repelling voids. The universe will be a cold, dark, and profoundly lonely place, with the last stars burning out and the final black holes evaporating into nothingness. This is the ultimate fate dictated by dark energy's victory in the cosmic tug-of-war, a quiet and eternal end to the vibrant, structured universe we call home. Our motion through the cosmos is not a simple pull toward a single point, but a complex drift shaped by an entire landscape of gravitational hills and valleys. The Great Attractor pulls and the Shapley Supercluster pulls even harder, but there is another, more subtle force at work, a vast cosmic emptiness that actively pushes us away. This is the dipole repeller, a colossal void whose profound lack of mass creates a gravitational effect all its own. Think of it like being on a raft in a large pond. If there is a powerful whirlpool ahead, you will be pulled toward it. But if there is also a massive, empty region behind you with very little water, the higher water pressure around you will actually push your raft away from that emptiness and toward the whirlpool. The dipole repeller is that immense, empty region of space. It is a cosmic desert so vast and underdense that its weak gravity cannot compete with the powerful pull of the mass concentrations around it. Instead, the collective gravity from all the matter-rich regions surrounding this void effectively pushes galaxies outward, away from the nothingness. We are not only being drawn toward Shapley and the Great Attractor, we are also being actively repelled by this great nothing behind us. Our journey is a product of this precise balance, a delicate tug of war between the something and the nothing. Other nearby superclusters add their own subtle tugs to this cosmic dance. Structures like the Perseus-Pisces supercluster exert their own gravitational influence, gently steering the local flows of galaxies and adding complexity to the river-like motion of our local universe. This intricate interplay means our path is not a straight line, but a winding course through a gravitational terrain made of the universe's greatest concentrations of mass and its most profound emptiness. So if our motion is the result of this precise cosmic balance, what would happen if just one of these immense players were to suddenly vanish from the equation? Our current map of the cosmic web is about to be rewritten. We stand on the brink of a new golden age of discovery, propelled by a generation of mega telescopes that will see farther and clearer than ever before. The Vera C. Rubin Observatory, with its immense camera capable of capturing the entire visible sky every few nights, will not just find new galaxies, it will watch the sky in motion. Over a decade, its legacy survey of space and time will create a colossal time-lapse movie of the universe, tracking the subtle movements of billions of galaxies. This will allow us to trace the gravitational currents flowing toward the Great Attractor with a precision we can only dream of today, potentially revealing hidden tributaries and unknown streams within our own supercluster. But to understand the true nature of these structures, we must look beyond visible light. The James Webb Space Telescope, with its infrared eyes, is our key to peering into the dusty hearts of galaxies hidden within the Zone of Avoidance. It will dissect the star formation and chemical composition of these obscure giants, telling us their history and mass, and finally giving us a complete census of the population that makes up the Great Attractor's core. And then there is the sheer audacity of the Square Kilometre Array, a radio telescope network spanning 2 continents. By mapping the neutral hydrogen gas that permeates the cosmos, the SKO will trace the cosmic web itself, charting the vast dark matter filaments that guide the galaxies. It will measure the peculiar velocities of millions of galaxies with breathtaking accuracy, potentially settling the debate over the dark flow once and for all and revealing whether our entire universe is truly drifting towards something beyond the horizon. Together, these instruments will transform our static map of the cosmos into a dynamic, living simulation, revealing the full story of our place in the flow and exposing secrets of the large-scale structure we have not yet even thought to question. What invisible giants will their powerful gaze reveal, waiting just beyond the edge of our current understanding? This grand cosmic architecture, from the Great Attractor to the flowing web of galaxies, forces a profound shift in perspective. We are confronted with the reality that our entire world, our entire history, and our entire species exist on a planet orbiting one star among hundreds of billions in a galaxy that is itself just one tiny leaf in a vast, flowing cosmic river. The existence of these immense structures does not make us insignificant, but it does redefine our significance. We are not the center of the universe, but we are a part of it that has become conscious, a part that can look out and begin to trace the outlines of the very forces that guide its path. This is a deeply humbling realization. It tells us that the universe operates on scales and according to rules that are far beyond our everyday experience, governed by dark matter we cannot touch and dark energy we do not understand. Yet, instead of stifling curiosity, this humility ignites it. Every mystery, from the Great Attractor's hidden heart to the dark flow's impossible pull, is a direct challenge to our intellect and our imagination. They are cosmic puzzles left for us to solve, driving the most fundamental human quest, the need to understand where we came from, why the universe is structured as it is, and what its ultimate fate will be. Our journey to map the Great Attractor is more than a scientific endeavor. It is the latest chapter in an ancient story, the story of a species looking up at the stars and refusing to accept that the deepest truths are forever beyond our grasp. These immense structures leave us with profound and unsettling questions. Why is our universe so lumpy? The cosmic web is a beautiful tapestry, but its very existence seems to contradict the cosmological principle, the long-held belief that on the largest scales, the universe should be smooth and uniform. The Great Attractor, the Sloan Great Wall, the Hercules Corona Borealis Great Wall, these are not minor features. They are colossal mountains and continents in a cosmos that was supposed to resemble a gently rolling hill. Their sheer size forces us to ask if the principle is merely an approximation, a useful simplification that breaks down when we finally see the true grandeur of the cosmic landscape. Or perhaps these structures are telling us something vital about the universe's explosive birth. The seeds for this lumpiness must have been planted in the first fleeting moments of the Big Bang, in a period of hyper-expansion called inflation. The pattern of the cosmic web is a fossil, a frozen echo of those quantum tremors from the dawn of time. The Great Attractor is one of the loudest of those echoes, and by studying its mass and its pull, we are effectively listening to the whispers of creation itself. This leads directly to the two greatest mysteries in all of physics, dark matter and dark energy. We feel the gravitational hand of dark matter pulling us toward the attractor, and we see the repulsive push of dark energy trying to tear the cosmic web apart. We have given these forces names, but we have no idea what they truly are. Are they new types of particles or a fundamental property of space itself? The Great Attractor is not just a destination, it is a natural laboratory. Its immense gravitational field acts as a lens, magnifying the effects of both dark matter and dark energy, allowing us to measure their influence with unparalleled precision. By mapping the flow of galaxies into this gravitational basin and weighing its true mass, we are conducting a grand experiment. We are testing the very laws of physics on a scale that no particle accelerator on Earth can ever match. Every galaxy pulled toward this hidden heart is a data point in our quest to understand the dark universe. The journey to solve the mystery of the Great Attractor has become a journey to solve the mystery of everything, from the universe's lumpy beginning to its dark and empty end. We have traveled from the hidden heart of our own supercluster to the edges of the observable universe, uncovering 30 secrets woven into the fabric of reality. We discovered our own motion, a million-mile, and our rush toward a cosmic blind spot. We learned to see with new eyes, piercing the zone of avoidance to find not a single monster, but a vast metropolis of galaxies, the Supercluster, at the gravitational core of Laniakea. We mapped the true scale of our home supercluster and felt the even greater pull of the Shapley Supercluster, the true heavyweight of our local universe. We traced the ghostly architecture of dark matter, the true engine of the cosmic web, and explored the vast filaments and repelling voids that define its structure. We confronted impossibly large walls like Sloan and Hercules and pondered the eerie drift of the dark flow, a motion that may point to realms beyond our own. We felt the counterweight of dark energy, the force that will ultimately dissolve the web, and we used the universe's own frozen ripples, the baryon acoustic oscillations, to weigh the cosmos. We saw how black holes sculpt their domains and how our entire cosmic distance ladder teeters on the precise measurement of these flows. From the great nothing of the Boots void to the digital universes we simulate, every secret reveals a cosmos of mind-boggling scale and profound mystery. This entire journey, from the first clue to the final frontier, is a testament to a single, powerful truth. Humanity, on a tiny world around a common star, has managed to map the invisible. We have felt the pull of forces we cannot see and traced the outlines of a reality built from dark matter and driven apart by dark energy. We are the universe becoming aware of itself, slowly deciphering the code of its own existence. The Great Attractor is more than a destination, it is a symbol of our endless curiosity. So, as you look up at the night sky, remember the silent, immense currents flowing through the darkness. Which of these 30 secrets reshaped your view of the cosmos the most? Share your thoughts in the comments below, and if you are ready for the next mystery, subscribe to continue this journey into the depths of space and time.